Good day to all of you. So, today we will look at the issue of current control in DC-DC converters. That is the topic of discussion for today. You remember in the last class, we had just begun the discussion on current control. Till now we have primarily been using the voltage feedback to compare with a voltage reference, and the output, which is the error of the comparator, goes to the PI controller, which will ultimately control the duty cycle of the pulse width modulated signal that is fed to the power semiconductor switch of the DC-DC converter in order to control the output voltage. Now, the problem is to control the output current, and as we saw in the last class, it has advantages like paralleling multiple converters, and also issues like doing unity power factor converters, where you control the input current to the converter. We will of course have a discussion on that also later on, but right now to the concept of current control in DC-DC converters. So, here the central component is the inductor, and we want to control the current through this inductor L. So, this inductor may be on the input side in the case of the boost converter, or in the case of the output side in the case of the buck and buck derived converters, but the objective is to control the inductor current. Now, if you look at our control block diagram, and let me take the buck converter as an example. There is a switch. I am showing this as a regular relay switch, but actually it is a semiconductor switch. You have the inductor and you have a capacitor and a load which is external to the system. Now, this switch, semiconductor switch, is controlled by the controller which gives a PWM output, and we used to have here somewhere a voltage reference, and if this is V naught here, V naught is fed back plus and minus. So, V naught feedback is compared to the reference. The error passes through a PI controller, and this goes to a PWM modulator, which has also the input carrier frequency, and this gives an output which is pulse width modulated. And that will accordingly control the switched. So, this is the basic control block diagram that we had been using till now. Now, in order to do current control, we need to have one more loop called the current control loop, and that should be a fast acting loop, should be a high speed loop. So, what we do, we shall try to modify this control block suitably accordingly, and we will have one inner current control loop, which will be the fast acting loop. So, for this we need to do one more measurement. We need to measure the current, and let us say we want to control the inductor current. So, let us measure the current which is flowing through the inductor. It could be at this point, you could measure, or you could also measure here. So, this current also will basically be a measure of the inductor current, and there are few other places also you can take the inductor current. You could also measure it here, which will give you an idea of the inductor current. Of course, this will be switched, it will be in this fashion, whereas here it will be continuous in this fashion. So, whatever, we will take this inductor current measurement and feed it to a comparator block, and let us say we get the current reference from the output of the PI controller block. Let us say this is the IL reference. So, this is plus and minus. Now, the compared output is now given to a flip flop, and it is an SR set reset flip flop. Okay. Now, let us say that this is the asserted loop, and let us say we have Q, and the output of that goes to your drive circuit to drive the switch. Now, this is an SR latch. Now, what do you give to the set? To the set, let us give a clock signal, and this clock signal is actually having a period corresponding to the switching period of the switch mode converter. So, this is the switching period, and on the positive edge, the SR latch is triggered. So, at every positive edge of the clock, the SR latch output goes high, at every positive edge. this will switch on the DC-DC converter switch. The inductor current will start rising, charging up. It will be rising, charging up. That is what is compared here. The moment this current goes above this reference, this becomes negative or goes low, and that will reset this SR latch, and this goes low. So, this basically is the current loop, is the inner fast acting loop. It is cycle by cycle control. Every switching cycle this will be active, and the power switch will actually turn off once the current in the inductor goes beyond a particular reference. So, this is how the current programming can come into the picture. So, in all current control, this would be essentially how the control block schematic would look like. There will be a inner current control loop actually being controlled using a SR latch kind of a or equivalent kind of circuit. There is a clock which actually defines the switching period of this power semiconductor switch. And then there is a reference which is actually set by the output of the slow acting voltage control loop. So, the slow acting voltage control loop, the PI output, will actually define what should be the reference current. Okay. Of course, in practical implementation there are few other modifications that will come in to address some problems in current control. We will discuss this later. Now, let us look at how the waveforms will look like here. Let us look at this waveform and this waveform, these 2 points. If you plot versus the time axis, now let us consider one switching cycle, meaning this is TS period. This is the on time and this is the off time of the DC-DC converter power semiconductor switch. So, during this time, the inductor current is rising, falling back, steady state, rising, so on. So, this keeps repeating, and this is the IL, the inductor current wave shape. And what is IL ref? The reference is the reference is just a DC like this. So, basically if I superpose both IL and IL ref, so let us say you have IL ref and now IL, the same waveform, if I superpose, you will see that the inductor current keeps rising. Then the moment the inductor current tries to go beyond IL ref, the SR latch is switched is switched and the output goes low, and the power semiconductor device switches off, and then from here it starts going low and the cycle repeats. So, this is the point of comparison for the SR latch, at which point it goes low and switches off the device. So, at every cycle, if you see, at this point the clock, rising edge of the clock switches the transistor Q on. And what is transistor Q? This is our transistor Q, the power semiconductor switcher. So, every cycle the clock appears here. So, the clock is a nice pulse, and then once the latch is SR latch is switched, so let me erase this portion and let us have two more access here T. Now, this is the SR latches Q output. The clock is going to appear every cycle at this time. And what happens to the SR latch? At this rising edge, this will go high. At the rising edge, this will go high. Now, as the inductor current is rising, at this point the inductor current goes more than the reference. The latch switches off exactly at this point, and so on, it repeats every cycle. So, this actually is the duty cycle modulation that occurs in the current control period, cycle by cycle. Okay, if all else is working fine, this would give you a very nice current control. However, there is a problem in current control which we will just now start to discuss in a short time, and that is related to this constant reference and also to the inductor current wave shape. So, these two give rise to an instability problem which needs to be compensated for, and this can be avoided if we do slope compensation for the reference. So, let us first see what this issue of instability instability is in current control. Okay, consider one period. Consider just one period. Let me zoom it so that it is clear. This is one period. Now, in this period, the inductor current is drawn in this fashion. And then it starts repeating every cycle, and this is the reference current. So, this is IL reference and this is IL. Okay. Now, let us bring in some perturbation. Now, let us say something happens due to so many uncertainties, anything can happen. The inductor current, instead of starting from here, it has jumped. Some perturbation came, it has jumped, and it starts moving like this parallelly. And from here it hits the reference, and therefore, the SR flip flop switches off and then starts moving parallelly here, keeps coming down till this point. When the SR flip flop now switches on, output goes high because the clock sets the flip flop, and so on, keeps going in this fashion. So, if there is a perturbance, so I will call this perturbance as delta IL. Now, this is a perturbance which is very likely in a practical circuit. These perturbances could come due to so many reasons. There could be a spike in the input voltage, which could perturb the IL for a short moment, and then that could carry on from there. Or there could be a change in the input voltage, which could probably change the slope. So, many of these issues can happen, and because of that, what we expect, the red colored waveform, could actually become the dotted blue colored waveform. Now, when the perturbance occurs and after the perturbance is removed, it is natural to expect that it should come back to the original red colored waveform. Does that happen? So, now that is what we need to look at. If it comes back to the original expected red colored steady state wave shape, then you know that the perturbance has been rejected and it is in a stable state. Now, let us look at 2 points. Now, in this one cycle, if there is a perturbance at the input, the difference between the steady state expected inductance current and the perturbed inductance current at the end of the cycle is this much. So, let us call that one as delta IL at the output and delta IL at the input of the period, at the start of the period. No, we shall probably change the delta IL at the start of the period and delta IL at the end of the period. So, we know the slope here. Now, let us say this slope is m1 and that is equal to m1 slope we know is equal to delta IL, the inductor current, by delta T, and that is nothing but delta IL by dTs, as this is the dTs period and this is 1 minus dTs portion of the period. And then what is m2? Let us say this is m2, and what is m2? m2 is delta IL, it comes down by the same amount, this is m2. Let us take the steady state waveform, divided by delta T, which is 1 minus dTs. And of course, there is one other term which will come in, which is the negative sign, because this is a falling slope. Now, if you take the ratio of m2 to m1 and take the absolute value modulus, so that the negative sign does not come into the picture, you have d by 1 minus d. So, what it would also mean is if I am having a perturbance delta IL at the start of the period, then at the end of the period, here what would you get? This would be the slope, because there are two slopes coming to the picture, m2 by m1, d divided by 1 minus d into delta ILS. So, whatever perturbation occurred at the start of the period goes through the whole period with these two different slopes and occurs at the output as a perturbation here, which is changed in amplitude with respect to the one at the start of the period by this factor d by 1 minus d, which is basically related to the slope. So, now what happens? Delta IL at the end of the period is equal to d by 1 minus d delta IL at the start of the period. This is the perturbance at the end of the period. So, the perturbance at the start of the period being multiplied by d by 1 minus d will actually decrease if d is less than 0.5. So, for less than 50% duty cycle, any perturbance here actually gets scaled down, attenuated, and the perturbance at the end of the period is reduced. So, this is reduced if d is less than 0.5. So, this becomes the perturbance for the start of the next period, which will further reduce in the following period, and so on. It will asymptotically reduce till the perturbance is rejected. Therefore, we say for all duty cycles less than 0.5, the system is stable. So, if you take for example, the same problem of the inductor current. So, let us say the inductor current, we will take few more cycles to show 2 cycle, that is a 3 cycle. Now, this is slightly 50% duty cycle. So, to see the effect, let us make the duty cycle less than 50%, which basically means that I will make the off time more, go up, and more off time, and go up, and so on. Now, in this time, if you take this 2 cycle period, this is one Ts, this is another Ts. Now, let us say the reference is set like this, IL reference, and now by some reason, for some reason, the perturbation has occurred here. So, it starts moving like that. And starts moving like this, starts moving like that, and so on. You will see that the perturbation will start decreasing. This would be delta I L E, which will be, this magnitude will be less than this magnitude, because the duty cycle is less than 0.5. Then the perturbation here, this magnitude will be less than this magnitude, because duty cycle is still less than 0.5, and so on. The magnitudes at every succeeding period starts reducing, and the disturbance is ultimately rejected. Now, let us take the case when the duty cycle is greater than 0.5. So, if duty cycle is greater than 0.5, then what happens? This factor is a number which is greater than 1. So, any perturbance at the start of the cycle, start of the period, would actually get amplified and appear at the end of the cycle, and so on at succeeding cycles, and therefore, it will go into an unstable situation. the perturbance is never rejected even after the removal of the perturbance. So, this will grow. Now, this is a dangerous situation, and therefore, this is something that is not desirable. So, let me quickly draw the wave shape here, T. So, this is our inductor current. I am trying to show the duty cycle is greater than 0.5. This is the current reference, and now we have the perturbance which will this perturbance will be greater in amplitude than this. And this will further increase at the start of the next cycle, and so on. This will keep increasing and keep growing, and as a result you will see the wave shape, current wave shape is in this fashion. You can recognize that this is an unstable situation, which will lead to pulse missing and incorrect inductor current wave shape and incorrect current programming. Therefore, we need to make a correction which will try to make the system stable even if the duty cycle is greater than 0.5. So, what is it that we try to do? We try to attack the problem in this fashion. Let us say we have this greater than 0.5 duty cycle. I am showing a duty cycle which is greater than 0.5, something like that. Now, this was supposed to have been the reference like this. Now, assume that we have the perturbed signal which goes in this fashion. Now, what would happen if the reference itself was having a slope like this? If the reference is having a slope like this. So, what would have happened? We would see that the perturbed current goes on like this and then takes a turn at this point. And you see that it is much less than what it was with a reference which is having 0 slope. So, going along in that fashion, if I modify the reference such that it is having a slope in line with the falling slope of the reference is such that it is having falling slope like that. Then, so let us say for example, the reference is in this fashion. It continues like that, and let us say it goes back, then continues like that in some fashion. Let us say the reference goes in this fashion. So, what would happen? This would go up to this point, the inductor current compares with the reference, switches off, and then the inductor current and the reference both are coming together like that. And in one cycle, you see that the correction is happening and the error due to any perturbation at the beginning of the cycle becomes 0. So, this is basically what we will be trying to do. We will be compensating for the slope of the negative slope of the inductor current and applying it to the reference such that the perturbation is eliminated, is rejected in just one cycle. So, therefore, the reference IL reference, instead of being just a DC like this, it is now modified to be in this fashion. It is having an inverted sawtooth shape, and what is the slope of this? This will be same as the falling slope of the inductor current. It should be same as the falling slope of the inductor current. I will put it like this, same as falling slope of the inductor current. So, which means that if you have an inductor current which rises like that, compares at this point, switches off the switch and then falls like this, and then the inductor current compares, falls, and let us say there is a disturbance, it will go like that and then falls like that, and then gets. So, whatever may be the duty cycle, this will be a stable solution and the disturbance is rejected within a cycle. This is a disturbance, perturbance. So, giving this kind of a compensated reference, a reference which is changed in slope, the slope same as the falling slope of the inductor current, is called slope compensation. So, giving a reference like this is called the slope compensation. And it is essential for all current control application where the duty cycle can go greater than 0.5. If the duty cycle is less than 0.5, you do not need slope compensation, because anyway d by 1 minus d is going to be less than 1, and it will anyway attenuate all the perturbance and reject it eventually. But to be on the safer side, giving a slope compensation in this manner is very essential and recommended. So, let us see how the control block diagram looks like now, complete. We had initially V naught reference, a V naught feedback, goes through a PI controller, and this will give the current reference IL reference, and this is passed through a comparator, plus and minus. We shall compare with IL feedback, and the output of this pass through appropriate Schmidt triggers is given to a set reset flip flop, set reset flip flop. The output Q. Now, at the set point, you are giving a clock, which actually tries to set the SR latch every cycle, and this goes to the drive, and then into the plant. Which is composed of some DC-DC converter, and let us say we have the buck converter for now, could be boost converter or any isolated converter, in this fashion, where the switch is controlled here. You have the inductor current being sensed, and you have the output voltage, which is sensed, passes through the sensing circuitry, and comes in like. So, this would be the total schematic, but now here we are making that modification of giving slope compensation. So, let us say the IL reference is getting changed slightly. We shall put one block just before and then add. So, this is plus and this is also plus. So, to this let us add an inverted sawtooth 0, and this is a DC, and here you will have a DC plus that inverted sawtooth, which actually goes like this, which is level translated. And this forms the reference, which is actually compared with this one. So, this would be IL ref, which will be compared with the inductor current to get the slope compensated. So, this portion what we are doing is slope compensation and this is the slope compensated current controlled DC-DC converter, which has an inner fast acting current control loop and outer slow acting voltage control loop, and there is slope compensation here, and this can be applied for any DC-DC converter without loss of generality. Now, let me just show implementation of the simulation for the case of a buck converter, how it is simulated. So, if this simulation PC, which is basically showing the schematic on GSM, GEDA GSM. Observe here, this is nothing but a buck converter. I am having two sources here. One source is the DC source of around 200 volts, and you have a power switch, semiconductor switch. This is the buck converter circuit. There is a voltage source with value 0, which is used as current sense. This is the output node, and we see this is the node just before the inductor. The voltage across the inductor is nothing but when the switch is on, V in minus V naught, and when the switch is off, it is 0 minus V naught. Now, this is a regular buck converter. Now, this switch is controlled from this controller. Right now, I am using just only the inner current control. The outer voltage control loop is not there. So, if you look at this, let us zoom in. You see that there is a SR flip flop, the output of which is going to the gate drive of the switch, buck converter switch. There is a clock which has 10 kilohertz setting, duty ratio of 0.1, 10%, very small duty ratio. This is used only for triggering the phase of 0, triggering this SR flip flop every cycle. Now, to the reset pin is connected the comparator output from these 2 points. This is basically the measurement from the current which is fed back from the inductor. This is actually a B source, wherein you can put in an equation. You see the equation here is a voltage which is proportional to the inductor current, VIL source. And what is that VIL source? It is something like this. This is the VIL source. So, a voltage which is proportional to the current that is flowing through this. It is acting like a current sensor. Now, coming back to this control block diagram here. So, this is actually the feedback current IL, and this point is actually the slope compensated current reference. So, you have a constant current reference here, and based on the slope of a current which is proportional to the negative slope of the inductor current, V naught by L, is fed through this current controlled source CCCS, and the current through this is used to charge up a capacitance. So, the voltage here is exactly same as the current which is proportional to the negative slope of the inductor current, and that is actually subtracted from this DC, so that you have a falling slope. And every time the clock sets this SR flip flop, it also switches on this switch which will discharge the capacitance, so that you get a sawtooth, inverted sawtooth kind of a thing. So, this is the slope compensated reference, and that is used to obtain the comparison with the measured waveform, measured inductor waveform. So, this is the entire buck converter current control circuit with only inner current loop control. Let me execute that using ngSpice. So, I will run the simulation, it will be quick. See. So, on running the simulation, now we can look at two waveforms. Okay, first the voltage, the output voltage. So, the output voltage is building up to something like that, around 80 to 90 volts. And what we are really interested is in the current control action. Is it really doing the current control? So, let us look at two important waveforms, the current reference and the inductor current itself. So, you see a waveform like this. Let me come to this portion later. Let us look at the steady state portion. So, you see that somewhere here we have the steady state. Let me zoom that. Look at this waveform. This is the red one is the voltage which is proportional to your IL reference, which is something like an inverted sawtooth. Look at the reference, it is a 15 amp reference from 15 amp, and this flat portion which you are seeing here is due to the pulse width of the clock. For the amount of the pulse width of the clock, the capacitor is discharged and you see the falling ramp. And when the inductor current rises and meets with the falling ramp, the SR flip flop is switched off and the inductor current starts falling down like that. So, that is the issue. If you look at the initial response, during this period, see that we have provided a 10% duty ratio for the clock. So, the inductor current will rise for the 10% time, then fall, so on, keeps rising till it overcomes the transients and then starts going to the steady state. This can also be controlled by giving a soft start or decreasing the clock duty ratio to much smaller, like 1%, because it is only the positive edge that is needed to trigger the SR flip flop. So, you can see that this portion, the current rises, the inductor current rises only during the portion of when the clock is in existence, and then after the clock goes off, because the current is higher than the reference current, this will start decaying immediately. So, this way you can achieve current control and then with an outer voltage control loop, you can get both the current and the voltage control. With this, we shall conclude, and the next class we shall use this principle of current control to look at power factor improvement. Thank you.